Look at this image. A man irons clothes strapped to a moving taxi. When asked what is unusual, Open Flamingo says he is drying clothes. Blick 2 notes a man sitting on a cab, but LLaVA deduces the context, identifying the makeshift setup and explicit safety risks. In the text-only domain, developers transformed base language models into highly capable conversational assistants, like Vicuna and Alpaca, through instruction tuning. They trained the models on thousands of examples of humans asking questions and receiving helpful answers. Replicating that success in the multimodal space stalled. Current models can describe objects in a frame, but they struggle to follow complex visual instructions or answer deductive questions about an image. Without hundreds of thousands of conversational image-text examples to train on, foundation vision models remain blind to complex human intent. Researchers have access to massive image-text datasets like LLaVA and conceptual captions. However, these datasets consist primarily of flat, single-sentence captions. They describe basic visual contents, but they lack conversational depth. The traditional solution is human annotation, but paying humans to write high-quality, multi-turn conversations about hundreds of thousands of individual images is prohibitively slow and expensive. The creators of LLaVA bypassed this human bottleneck entirely. They used a text-only language model, GPT-4, as an automated synthetic data generator. This presents an immediate architectural paradox. How do you teach a text-only model like GPT-4 to analyze an image it cannot physically see? Converting these visual signals into language tokens bridges the gap to a general-purpose multimodal assistant. Researchers translated physical images into symbolic text. They fed existing captions and bounding box coordinates to GPT-4 as text context. This encodes spatial locations and concepts, like a person or backpack, into a sequence a language model can parse. With these symbolic strings as input, researchers prompted the text-only GPT-4 model to output text as if it were directly looking at the image. This generated 3 data types. First, multi-turn conversations with diverse questions and answers. Second, detailed single-turn descriptions mapping out the scene and object relationships. Third, complex reasoning tasks requiring step-by-step logic based on bounding box and caption constraints. Through this automated pipeline, the team generated a highly diverse 158,000 sample dataset, completely eliminating the need for human annotators. Constrained by accurate symbolic coordinates, text-only hallucination provides a highly scalable proxy for multimodal ground truth. With the synthetic data generated, the next step is building the physical neural architecture required to process it. This schematic illustrates the model's structure. It relies on 2 pre-trained pillars, Vicuna as the language model and Clip VIT-L14 as the visual encoder. Connecting a vision encoder to a language model typically involves heavy, complex mechanisms like gated cross-attention layers or Q-formers. LLaVA uses a radically minimalist solution, a simple, trainable linear projection matrix, denoted here as W. This matrix converts the raw visual features extracted by Clip directly into language-aligned visual tokens. This relies on a strict mathematical constraint. The linear projection ensures these new visual tokens share the exact same dimensionality as the language model's native word embedding space.
Because they share that same dimensional space, both the visual tokens and the standard text instruction tokens feed seamlessly together into the frozen Vicuna language model. This lightweight bridge proves that massive architectural overhauls are not required to achieve deep multimodal alignment. To protect the pre-trained weights of Vicuna and Clip from catastrophic forgetting, the researchers implemented a strict 2-stage training curriculum. Stage 1 focuses entirely on pre-training for feature alignment. As shown in the architecture schematic, during this first stage, both the Clip visual encoder and the Vicuna language model are completely frozen. Only the projection matrix W receives updates. It is trained against 595,000 filtered image-text pairs. This stage functions as a visual tokenizer. It teaches the matrix how to map basic visual concepts directly into Vicuna's existing vocabulary. Once aligned, the model enters Stage 2, end-to-end fine-tuning. The language model is unfrozen, allowing it to learn directly from the 158,000 synthetic conversational examples generated by GPT-4. Isolating the baseline feature alignment from the complex instruction tuning protects the model's foundational knowledge, allowing it to safely absorb high-level reasoning. The effectiveness of Stage 2 comes down to the specific mathematical objective utilized during fine-tuning. Look at the data structure. The training sequence contains a system message, human instruction, and assistant answer. System messages and user questions serve purely as contextual grounding. The actual prediction targets are exclusively the assistant's generated responses and specific stop tokens. The autoregressive probability equation computes the model's likelihood of predicting those target answers, one token at a time. The critical rule here is that the loss penalty is only computed on the assistant's prediction tokens. This mathematically forces the model to ensure all generated answers are grounded in the provided image context. Penalizing only the generated answers ensures the language model learns to actively follow instructions rather than passively memorizing the input text. To test the limits of this training curriculum, researchers evaluated LLaVA against the rigorous Science QA benchmark. They employed a novel model ensembling technique, using GPT-4 as an automated judge to evaluate both its own text-only output and LLaVA's multimodal predictions and settle any disagreements. This synergistic approach achieved a state-of-the-art accuracy of 92.53%. Beyond benchmark scores, the model demonstrates emergent behaviors, like recognizing completely out-of-domain visual concepts. Look at this portrait. LLaVA correctly identifies Elon Musk from a visual input, despite the fact that he never appeared in the alignment or instruction tuning datasets. Because the minimalist projection grid translates vision into the LLM's native language space, the base model's vast textual knowledge successfully generalized to unseen visual domains. LLaVA's success stems from prioritizing high-quality synthetic instruction data over structural complexity. A simple linear matrix, combined with a GPT-4 translation pipeline, effectively bypassed the multimodal annotation bottleneck. This establishes a new feedback loop in machine learning, where strong textual models construct precise data needed to train the next generation of visual models. Artificial intelligence will advance as we leverage current aligned models to autonomously train their successors.